Right, so last lesson, we looked at the mechanism for halogenoalkanes. Halogenoalkanes tend to go through nucleophilic substitution reaction. Sorry, you've already seen the criteria for a nucleophile. It needs to have a lone pair of electrons that it can donate. And there are two types of nucleophilic substitution reaction, the SN1 and the SN2. The SN2 is usually for your primary halogenoalkanes. So what happens is that in the first step, or what we call the slow step, you have both the nucleophiles and the reactant. Okay, so there are two species, hence the SN2. The next one that we're going to look at is SN1. That means there is only one species in the slow step of the reaction. So that means there must be two steps in the mechanism. Okay, so just to recall back again, the carbon-bromine bond is polarized because there is a difference in electronegativity between the carbon and the bromine. Bromine is higher in electronegativity compared to carbon, so bromine becomes delta minus, carbon becomes delta plus. As the lone pair of electrons is being donated from the oxygen, this means that the carbon and the oxygen will form a new bond. This means that the carbon would have 5 bonds. Okay, in order to make the carbon to only have 4 bonds, one of the bonds need to be broken, the original bonds. And usually it is the weakest bond or the bond with the smallest bond energy, and that is the carbon-halogen bond. In this case, it's the carbon-bromine bond. So when this bond breaks, the electrons in the bond will have to go somewhere, and nicely enough that these electrons can go to the more electronegative element, which is bromine. So when bromine owns the electron pairs, it then becomes the lone pair. Okay, so bromine goes from slightly negative to become fully negative, full negative charge. So then you have a transition state where it shows the bond that is currently forming and the bond that is currently breaking. We usually use dotted lines instead of solid single lines so as to not confuse or make it look like the carbon has 5 bonds. Okay, so the dotted bond shows that it is in the process of forming or in the process of breaking. This is called the transition state. Don't forget the negative charge of your nucleophile. If your nucleophile is neutral, then there won't be any charge. Sometimes you will see that this charge is being placed outside the square bracket. It doesn't matter. Okay, the product that you get will be an alcohol. So it will be an alcohol that is derived from the original halogenoalkane. So if you started with a bromoethane, then you will end up with ethanol. Yes, Daniel, do you have any question?
Miss, for the transition state, do we need to label bond forming sama bond breaking?
No need. You can just draw the dotted bond.
Okay, thank you.
You're welcome. Okay, so in the exam, if you're asked to draw the mechanism, you do not have to write down the bond forming and the bond breaking, okay? So the dotted bond is enough to show that they are in process. Okay, moving on. So this works with any tertiary halogenoalkane. SN2. Okay, so this works with any primary halogenoalkane, and it works with any nucleophile. Okay, as long as you follow the steps, then everything should be okay, should be correct. Okay, the next type of mechanism, the second type, is the SN1, which is usually for the tertiary halogenoalkanes. Okay, so the tertiary halogenoalkanes, you've learned about classifying these different halogenoalkanes. It is when you have 3 alkyl groups attached to the carbon that is attached to the halogen. Okay, so 3 alkyl groups attached to your CX bond. I will show you in the next slide. S stands for substitution and for nucleophilic, and the 1 indicates that only one reagent or one reactant is involved in the slow step. Okay, so for now, you don't have to worry about what is the slow step or what is the rate determining step. Okay, so the example I'm going to use, a simple tertiary halogenoalkane example that I can use is this. Okay, and don't forget, the moment you see halogenoalkane, you should make it a habit to know that the carbon halogen bond is polarized. Carbon bromine bond is polarized. Okay, so here's an example of a tertiary halogenoalkanes. I've got alkyl groups attached to that carbon. This is called a 2-bromo 2-methyl propane. Okay, right. So what happens is that it's a little bit different from SN2. Okay, SN1 contains 2 steps. The first step is the breaking of the carbon halogen bond. So the CBr bond will break. And of course, the electrons will always go to the more electronegative atoms. In this case, it's the bromine. So you will form, I will start with the bromine first because that's the easiest. Since the bromine owns, okay, or fully own the electron pair, which is now becoming a lone pair, okay, so it will become a negative species. Okay, so it goes from slightly negative to become fully negative. So this is something also students always get confused. Okay, because sometimes they forgot to change the bromine. They write it as delta minus instead. So the other product you will get is, since the carbon lost its electrons, carbon did not get the electrons, carbon should develop a full positive charge. Okay, so it goes from slightly positive to become fully positive. And this is called a carbocation, if you still remember from the previous topic, and specifically they are the tertiary carbocation because it is attached to 3 alkyl groups and the alkyl groups are just 3 methyls. Okay, this first step is called the rate determining step, or we say that it is the slow step. In some textbooks, you will see that the slow step is represented by a reversible arrow. Okay, so I will not go into details on the reversal arrow. Hello, Abigail.
Hi, I'm sorry, miss.
It's okay.
It's okay.
All right. Abigail sounded like she was crying. Okay, so tertiary carbocation will be formed. And if you remember again from the previous topic, tertiary carbocation will be the most stable, followed by the secondary, and the primary carbocation is the least stable. So the fact that I have mentioned the primary carbocation being least stable should already tell you why primary carbocation cannot go through this mechanism. Okay, I'll show you that later. Okay, the next step is then your nucleophile coming into attack. Okay, so please don't do this, because if you do that, then basically you're just going back to the start. You want your nucleophiles to attack. So your nucleophile is your hydroxide ion. And again, most important for you to draw correctly where the lone pair is sitting on, which atom. Okay, because that's how you will form your new bond. So this lone pair of electrons on oxygen will be given or shared with the carbon with a positive charge. So then it forms a new bond, which is the CO bond with carbon. If you draw your lone pair of electrons on hydrogen, it looks like the carbon is forming a bond with hydrogen. Okay, and that is wrong. So that is your new bond, carbon-oxygen bond. So you see the products, the product is still an alcohol, right? It's the same. You will still get an alcohol product, just like you would with SN2, right? The only thing that's different is the steps, the method. And your other product would of course be just the bromide ion. Okay, so to name this, we call this 1, 2, 3. So that's a propan-2-ol. The second position is to indicate where your hydroxy group is. And then you have a methyl group on the second carbon. So that's 2-methyl propan-2-ol, one word. Okay. Right. So this is then, so you may copy this down slow and fast. Okay, so don't worry about the slow and fast, the rate at the moment. So this first step is here, happening here, okay, where the carbon-bromine bond is broken. And then the second step is happening here, where the nucleophile comes into attack. So you should learn the steps, memorize the steps, but don't memorize the molecule, okay? Because you can always change the molecule. You can always use a tertiary chloroalkanes or a tertiary iodoalkanes. And then you can also use the different nucleophiles, cyanide ion, water, ammonia. Okay, these are all different electrophiles, nucleophiles. For the next section, while you're still copying down, I'm just going to explain to you why primary carbocation cannot go through SN1. Okay, so imagine if primary halogenoalkanes were used. Okay, then I would just use a simple halogenoalkane. So that is an example of a primary halogenoalkane. Then the carbon is slightly positive, bromine is slightly negative. Same thing, the carbon-bromine bond breaks, and this is the slow step. Then I form a primary carbocation. Primary carbocation is unstable. So that's why it does not go through SN1 mechanism. So we've looked at the two extremes. Okay, I haven't talked about the explanation yet. Okay, why carbocation ion only forms with tertiary halogenoalkanes but not with primary. That will be covered in the next slide. Okay, so I've covered the both extreme ends. The most stable carbocation ion will go through SN1. The least stable carbocation ion cannot go through SN1, so it has to go through a different route, which is SN2, which is the one that we looked at in the previous lesson. What about the secondary halogenoalkanes? The secondary halogenoalkanes can choose. They can choose SN1 or they can choose SN2, okay? No problem. Or they can even get a mixture of both mechanisms. Okay. Are you done copying this down?
Yes.
Okay. Thank you, Ayman. Daniel, you still have your hand raised up.
Oh, okay.
Thank you. Okay. Right. So this is, well, almost there. That's not the explanation yet, okay? But tertiary carbocation ion has 3 alkyl donating groups. That means you have more positive inductive effect attached to the positive carbon. Therefore, the carbocation ion is the most stable, okay? Well, okay, I guess you can copy this down for the explanation to why tertiary halogenoalkanes form carbocation ion, but not primary halogenoalkanes. Okay, the diagram you don't have to copy down. Well, I guess you could. Okay, so please copy this down now. Okay, so that explains why only tertiary carbocation ion can go through SN1 mechanism, okay, because of the stability. Okay, for secondary halogenoalkanes, I've already mentioned this to you. Right, next, hold on. Okay, the next learning objective is to describe the following nucleophilic substitution reaction. So we're now using different reagents, okay? So reaction with sodium hydroxide, that is basically when your hydroxide is your nucleophile, okay? So you can use sodium hydroxide or potassium hydroxide as a source of your hydroxide ions. And to produce alcohol. The second reaction is with potassium cyanide. So that is your source of cyanide ion. You can use potassium cyanide or sodium cyanide, but the condition is that it has to be dissolved in alcohol. Usually you use ethanol. We call this ethanolic potassium cyanide. The reaction with the reaction with potassium cyanide in alcohol or ethanolic cyanide is to produce a new functional group called the nitrile. The next one is using ammonia. So ethanolic ammonia, we do not use aqueous ammonia. The reason is that if you use aqueous ammonia, then the water molecule in your aqueous form will be the nucleophile. So that's why we want to use ethanol. Okay, we don't use water to dissolve them. Likewise, for potassium cyanide, if I use potassium cyanide aqueous and the aqueous contains water, water is the nucleophile. So the water will attack my halogenoalkanes, not the cyanide nucleophile. Okay, so ammonia in ethanol, or sometimes called ethanolic ammonia, it has to be heated under pressure to produce a new functional group called the amine. Okay, so let's see. Now this next one, substitution with sodium hydroxide aqueous, is actually the same as the mechanism that I've drawn for you on page 4 and 5. Okay, so I will not go through that again, but there are a few things that I want to point out on this page. This process or this reaction is not called hydrolysis. Okay, so that's for water. So this is from the previous notes where I forgot to delete that because I've moved the reaction with water towards the end. And also this equation is wrong. So just change it, right? Instead of H2O, change it to hydroxide. So you start with any halogenoalkane to form an alcohol and an anion, which is your halogen that turns into a halide. Okay, so some students usually ask, what about the sodium in the sodium hydroxide? Well, sodium is just a counter ion. You can always add it and it will stay unchanged at the end of the reaction. So the sodium ion is just to counter the ions that you have. So as I said just now, you can use sodium hydroxide or potassium hydroxide, aqueous. Please make sure you label the aqueous state, because this is important, because there is another reaction of halogenoalkanes with your sodium hydroxide. However, the solvent is not aqueous. The solvent is ethanol. So if you don't write down whether it's aqueous sodium hydroxide or ethanolic sodium hydroxide, then your answer is vague and CIE can penalize you. Okay, it shows that you're not sure. Okay, so it's important for you to write down the solvent. Is it in aqueous or is it dissolved in ethanol? Right, the mechanism, I will not go through it again with you. I want you to try it yourself, okay, and check that you've got it correct. You've drawn the correct mechanism as the ones on page 4 and page 5. Okay, so before we, this will be the last one before we end this session. You will notice that most conditions of your organic reactions mention that it has to be heated under reflux. Okay, so reflux is this setup where you have a flask. That flask may be like pear-shaped or round bottom flask. That's where you put your reaction mixture. Okay, and then heating happens here. You will heat your reaction mixture. Okay, you will heat it here. And then you have a Liebig condenser. I don't know if you know a Liebig condenser, but it's the one that you use during distillation. Except that when you are setting up for distillation, the Liebig condenser is placed at an angle. Sideways, but at an angle. Okay. Here, your Liebig condenser is positioned in an upright position, or we say that it is arranged in a vertically. Okay. Now, why do we do this? There's also an opening here. Okay, so this setup is not fully sealed. So air can come in, air can come out. Okay, so why do we need the setup? Okay, for reactions, especially your organic reactions, most of your organic molecules are volatile. Volatile means they turn into gas easily. Okay, so what happens is that, for example, we take this as a reaction between bromoethane and sodium hydroxide. Okay, so then I form ethanol. So ethanol is a volatile molecule. So if I form ethanol gas, okay, so you would imagine the gas would evaporate. The gas would move up. Okay, so imagine this is a Liebig condenser. Oh, forgot to mention, in this Liebig condenser, there's water in and water out. The reason for this water in and water out is to make the Liebig condenser cold for condensation to happen. Okay, so back to my ethanol in gas form. Okay, so when my gas ethanol is traveling up, it then reaches this cold region. So in this cold region, my gas ethanol, my ethanol vapor will be condensed, will be transformed into liquid. So gas turns to liquid, liquid is heavy. What happens is that by the law of gravity, the liquid will fall back into the reaction mixture. So this will be a process. Some ethanol gas or ethanol vapor will want to escape, but when they reach the cold region, they turn into liquid, they fall back again. Okay, so that's why there's no need for you to seal this reflux setup, right? So that's what reflux is for. It prevents reagents from escaping. Any vapor, any gas molecules that want to escape, by the time it reaches the condenser, because it is cold, it is transformed into a liquid and it falls back into the flask, right? So why do we do this? Why don't we want the product to escape? Well, because we want to wait for the reaction to be complete. We want to make sure that all the reactants, all the halogenoalkanes in this flask is already converted into alcohol. Okay, so when you only form one alcohol, it wants to escape, it falls back. So this will be like a cycle. It goes up, it goes down, goes up, goes down, until you are convinced that the reaction has complete. Okay, so that's the best thing about reflux. You don't want to collect the products straight away. You want the reaction to be complete first. Okay, so you will not lose any volatile products. You will not lose any gas, because most of your organic molecules are volatile, and when they reach the condenser, which is a cold region, it turns into liquid and then it falls back. All right. Okay, so that is all for today. In the next session, so remember to fill this in, the SN1 and the SN2 mechanism. You can choose any SN1 and any SN2. Sorry, you can choose any halogenoalkanes for SN1 or SN2 as long as they are the correct type. SN1 must be a tertiary halogenoalkane. SN2 must be a primary halogenoalkane. Okay. Okay, any questions before we go?